So if the RAM is an address space, if it's storing memory, then what does memory look like in RAM? Well, I've shown you that the spin of an electron is effectively, let's say, representing a one, and the down spin is representing a zero. Well, what does this look like in more of an abstract rather than a physical way, as it were? Well, if we have let me draw a RAM module this way around, I think. Now, when we have this module, we'll break this down into different addresses. So, okay, let's say this can store 16 gigabytes of RAM, 16 gigabytes of information. What I'm going to need to do is first of all break this down into some kind of chunks. So some chunks of information will be broken into, let's say, I don't know, into 1 megabyte chunks. 1 megabyte chunks. And these 1 megabyte chunks might be broken down into, I might be able to have 5 megabytes for one piece of software, and I'll allocate it to the internet browser. The internet browser will have 5 megabytes of RAM, and inside that RAM then it will be broken down even further. So this is the software RAM. It's not this now. It's just like this little tiny part of it. So this is now broken down even further. And then we have the stacks and the heaps and the da-da-das. I won't go into this too much just yet. So what's going on in memory in general is that this bit I wanted to talk about, breaking it down into addresses. Well, these are actual addresses. They're logical, of course, and often nowadays random. Now, when I have an address, we like to call this section 0, and I might want to call that 1 and 2 and 3 and 4, 5, 6, 7, 8, 9, and 10 up there. So if I had an address space actually represented, you'll see this in something called hexadecimal. And just like binary, it's another base system, basically. It's base 16. So this one's base 16. Binary is base 2. Our numerics are, and normal is base 10, right? So how does hexadecimal work? Well, hexadecimal has 1, 2. It must have 16 characters, right? 1, 2, 3, 4, 6, 7, 8, 9. It's got A, B, C, D, E, and F. So that's 1, 2, 3, 4, 5, 6 plus 9. So that's 15 plus 0 is 16. So if I wanted to demonstrate what the number, let's say 14 is in hexadecimal, well, I know that's 9. This is 10. This is 11. This is 12. This is 13. This is 14. So actually, when I say this, when I give you this in hexadecimal, that means 14. When I give you an F, that means 15. When I give you an F and an A, when I say FA, that means, well, we've got 15 15s. So we've got 15 times 15 because it's in the tens column. We've got this units column again. So we've got 15 because that's the number 15. We've got 15 15s. Sorry. Yeah, 15 16s, not 15 15s. We've got 15 16s. And we need the A, which is, so plus, we need to do this. I'm just making the order of operations clear. And we've got an A, which we said was 10. So plus 10. So that's this figure plus 10. I could have a... Let's do an easier one. I could have this, a 1, 1A. Well, what does 1A mean? 1 means 1 times 16. And an A is a 10, which actually means that 1A is equal to these two here put together. So 1A is actually 26. And for me to just give you 1A and say what number is this, it's a bit complicated. It could be base 64. It could be a lot of different bases. So what I need to do is just do this and write an OX in front of it. This basically tells you that it's hexadecimal. So that being said, now let me go through the memory addresses. What we would actually have in this case, because memory addresses are given in hexadecimal, we would have 0, 1, 2, 0, and it would actually be 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, 1, all the way to F, 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 F. So this is bits. How many bits is it, and how does it matter? What does it matter? How do I know how many of these I've got? Well, this is where the whole 32-bit architecture and 64-bit architecture comes into play. At the end of the day, each one of these chunks is going to have to at some point go through the CPU. Now, when it goes through the CPU needs to be able to take in physical addresses. It needs to be able to take in physical amounts of information. It might be taking in, I don't know, 32 bits of information effectively at a time, or 64 bits of. It can compute this. You know, we've been through this this CPU architecture of bits and what it means. So what that means is it'll compute. It can take in 32 bits or 64 bits. Now, if I'm doing 64 bits and 32 bits, that also means that my address will be 32 bits long, right? 32 bits long, or it'll be 64 bits long. 64 is a lot longer than that, blah, 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 blah. So my beginning is a 64-bit or a 32-bit 0000, so 32 zeros or 64 zeros. And obviously in the 32-bit zeros, I'm going to have much less. I'm going to break this down into 32-bit spaces. Whereas if I had 64 bits, I'd actually be breaking it down way, way more. And you'd have much smaller chunks, and I'd have much more memory addresses, and I can do way more things. Now, this is very important. This is the last thing that I'm going to say, is that as you can see, as I'm drawing these things, I'm fitting quite a lot of these red lines, the 64-bit addresses, into one of these green lines here, the 32-bit addresses, right? Which means that I should be able to run a 32-bit application, a piece of software on a 64-bit, but I probably wouldn't be able to do the other way around. In fact, I know for a fact I wouldn't be able to do it the other way around, and simply because the 32-bit will run out. It'll get FFFFFFF for 32 times, and if I wanted an address on a 64-bit software that used 40 Fs, well, 32, that it will run out of memory, right? It's got to its maximum, so it cannot possibly do it. So when we're thinking about software, and we'll go into this a bit more in depth on compilers and stuff, but I need to know what kind of memory address sizes I'm using, because I might not be able to run a 32-bit software on some 64s, but usually you can, and you should be able to in theory, because effectively all 32s will fit into 64s, but obviously 64 won't fit into 32.